Anymore on collective. Like, for example, if you punch in collective and the tail wiggles out a bit to the left and then comes back, that one needs to go up, collective feed forward gain. It's the same as torque precompensation on a V-bar or any other flywheel system. Every single flywheel system. Videos on setup. Okay, most people, if not, you can search for Rotorflight setup Jonas and you will find them. They're on YouTube. They explain the entire process again if you want to see it again. I do a couple things a little differently. I do many things the same. So yeah, we are going from basically this point of having a helicopter that is set up and ready to go. So for the filter section, I just want to do a quick recap, if we actually have the time, because not everyone has seen the video and filter setup is very important. I'm just going to airdrop a little video over here. Not a video, a log. Robert's laptop, very good. And we're going to look at that log in the Blackbox Explorer, if it airdrops. Oh yeah, you need to accept it. Just like I said, this is kind of freestyle. Okay, can you open the Blackbox Explorer, please? Then I can quickly show them. Yeah, very good.
Got it?
Yeah, there it is. Cool. Can I pull this? Good. Okay, oh yeah, you already have things configured here. So I'm just gonna open the log that I just airdropped. Where is it? I would say don't disconnect it yet. Here, vibration. Okay, so filtering. Oh, I just dropped the thing. I'll go fast. Okay, so the entire point of filtering, why are we doing it? You have a gyroscope in your helicopter and that picks up rotation rates. Pitch, roll, yaw. I actually brought my little M2 Evo to demonstrate this. So you have a gyroscope that picks up pitch, roll, and yaw. The annoying thing about this is it also picks up vibrations from the main rotor, from the tail rotor, from the motor, from the gear train. And these vibrations do not contribute to flight performance, so we want to get them out. I am just going to stick tracking. This should have what I need. I'm just going to show you. I'm actually. Okay, so we are going to look at our pre-filtered gyros. Just want to show you what this looks like. So this is a flight that I did where I just flew. And you can see, maybe, that this is very, very noisy. You can see the yellow trace. It goes up and down and up and down. If I actually click this, I get this. It is kind of hard to see. I will try to scale it up a bit for you. You can see all these peaks. These peaks right here, they're all vibration. Some from the main rotor, some from the tail rotor, some of other things. And the idea now is to reduce these to zero. So if I just add the filtered gyros, I can show you what it should look like after this. You can see all the peaks are gone. And that is the idea behind filtering. We're leaving all the flight movement in the gyro signal, and we are removing all the noise. I explained this a bit more in depth in my video. All you need to know is if you have a helicopter that has a main rotor and a tail rotor, you come into the gyro tab and you're going to basically do what's already done here. You want a general low pass. A low pass is a type of filter that just cuts off vibration above a certain frequency. So for example, you have a, I don't know, 0 to, say, 15 hertz range of flight vibration. Then above that, somewhere starts the main rotor, maybe 30 to 60 hertz. And then the tail rotor starts at like 100 hertz or something. And this just cuts off all high frequency vibration that you don't want. So if we, oh, he has all that stuff disabled. So I'm going to go back manually. So in the frequency range, you might just cut off maybe, yeah, here, gyro low pass filter. Everything behind this line will be cut off. It is a bit more complicated than that, but you can imagine it like this. Then we have the dynamic notches. Dynamic notches, they're neat because they actually seek out frequencies that stand out the most, log onto these, and filter them out. The defaults of 4 notches at a Q of 2.0, that's amazing. You can leave that in. Nothing needed to modify here. Now, every modern ESC delivers an RPM signal. That is a neat little wire that comes from your ESC, plugs into the flywheelless unit, and tells it how fast is the motor spinning. And the thing that Bob showed earlier, where you set the gear ratios, that also tells the system how fast is my main rotor spinning, how fast is my tail motor spinning. And based on that, we can also filter these vibrations out. So what we have here are RPM-controlled notches. Main rotor fundamental frequency notch is the 1 per rev vibration of the blade of the main rotor. For example, if one of your blades is a bit heavier, that is going to create a vibration that comes around once per revolution of the rotor. That filters that one out. Below that, you have the second harmonic. The second harmonic is cyclic resonant flap. So if your blades flap up and down during the revolution, it filters that out. That is actually one of the main contributing factors of helicopter noise. Third and fourth harmonics are just different bending modes of the rotor blades. It doesn't really hurt to enable these. Most main rotors will show a third and a fourth harmonic, so just turn these on and you will be fine. That's these 4 here. Then you have the same for the tail rotor. The tail rotor, as I said, is higher in frequency. For this example, on the M7, it is 5 times faster than main rotor, so the frequencies are 5 times higher. You can just turn on the first and the second notch, and it'll take care of this. How you can test this is by just going up and doing a flight with logging. And in the log, you're going to look for continuous flips. So you want to do continuous flips. You can then limit the range with I and O. And then you will get a vibration spectrum that shows you what your helicopter is doing in continuous flips. You probably cannot see this very well. We have 100 hertz here, 200 hertz here, 300 hertz here. Everything that is really important to this is below 100 hertz. So I'm just going to scale this over a bit so you can see it better. Now the maximum is 167 hertz. You can see one peak, that is the main rotor fundamental vibration. This wider peak, I hope you can make it out, is the second harmonic from the resonant blade flat. Here is the third harmonic, this is the fourth, and here starts the tail rotor. And after filtering, it should look like this. All the peaks are gone, and you should be good. If that's the case, we can continue on to PID tuning, which is probably why most of you are here. PID tuning starts in the Profiles tab. You have this menu. It might look intimidating at first, but it really is not. You have... I have 5 minutes to do this, oh boy. I'm going to show this up here. You have proportional gain, that is your P gain. You have integral, that's your I gain. You have D gain, you have feed forward, and you have boost. One more gain that you will need is the high-speed integral. That is down here. It is not in the main section. We'll also need this. Okay, so what do these gains do? The P gain is a general correction. It looks at the rotation rate of the helicopter and counteracts that. The I gain is an integral of that. Integral means it looks at the angle. So for example, if the angle of the helicopter is 30 degrees off, it gives an amount of correction X. If the angle is 60 degrees off, it gives double that. It's proportional to the angle of the helicopter. D gain is a derivative of the rotation rate. So it looks at the acceleration of the helicopter. Helicopter is hovering, nothing is happening. Helicopter is rotating, nothing is happening. But as soon as you give an input that changes the rotation rate of the helicopter, for example, from a hover, you accelerate, or from a rotation, you stop, the D-gain counteracts that. Why is this important? Because it acts as a damper on the helicopter. Feed forward is pretty simple. If you give an input, it just puts that input right through to the swash without any control logic. Boost is basically a derivative of your stick. So if you move your stick, it gives a little boost to the swash plate so the reaction becomes sharper. And the high-speed integral, which I mentioned earlier, is especially important for fast flight. It basically makes it so that if you fly fast and give big collective inputs, the helicopter does not get into a porpoising motion, but climbs and drops in a straight line. So, how do you tune this? Because this is the most crucial part. To preface this, Joanne is not going to agree with me on this. He likes to just play with the gains and until he gets to a point where it's good for him. I tried to develop a method that basically everyone can follow. So what do we do first? Might start with P, might start with I. No, we're going to start with D, because D is the most sensitive gain and everything else depends on the D gain. So what do? These are actually slightly different from the defaults that Rotorflight comes with, but it doesn't matter. From the defaults, you will have D, I think, 10, 20, I don't know. These will be too low to fly, so you raise them. How far do you raise them? Assuming your filters are good, you can raise them to like 60, 70, 80. And by the point you're there, what you want to do is you want to simply climb and pirouette to the right. And if the helicopter starts shaking during that, you back off a little. Why do we do this? By climbing, we increase the inflow of air into the disc. That in turn increases the aerodynamic gain of the rotor blades, makes them more agile. So any overgains will show up first in maneuvers like this. And also because we're yawing right, we're increasing the rotor RPM because the governor does not know we're yawing. So that will tell you your maximum D gain. While you increase your D gain, you will notice that from being very wobbly, like defaults on Rotorflight will not stop well on the elevator axis. It will go to like being more crisp and not wobbling as much. And then it will become slower to react. That is okay, we're not done yet. So once you have found your maximum D gain, climbing up, it starts to wobble, back up 10, 15 points until it doesn't do it anymore. We are going to tune feed forward. Why? Because we now have a flyable helicopter, and feed forward plays a crucial role in how the control system reacts. Nope, you're not turning off on me now, because I need this one. Let me see if... stick tracking, yeah, that is the one I want. Okay, I just need a section of continuous flips again. Let's say we do the pitch axis. Okay, this is pretty zoomed in. Let me zoom out. Okay. You barely can see this, but if you look right down here, there's a trace. Maybe you can see this. That is my integral. We remember the integral looks at the angle of the helicopter and corrects it if the angle is not correct. So what do we do with our stick? We command a rotation rate. Or in other words, an angle change. So this integral wants to act if the helicopter does not rotate the way we want it to. There are some drawbacks to having the integral charge when we give inputs. So we want to tune feed forward so that the integral stays at 0. Basically, we make the helicopter flyable without the control loop. So the control loop has to do minimal work to fly the helicopter. In this example, I was just testing for vibration. My helicopter was not tuned well. You can actually see that the integral charges quite a bit up here. And that would mean that for the flips I'm doing, because this is continuous flips, the feed forward amount is too low. So what would I do? I will go in to feed forward and increase this value right over here until During continuous flips, the line of the integral in the black box log. Oh, Bob has export turned on. That's why it looked weird. So this line would stay at 0. Why is this important? Because then we have a helicopter that is basically flyable on feet forwards with the correct rates-ish. It's not gonna react perfectly, but the control loop has easy play to keep it under control. Now that we have done this, we're going to look at P. P gain is an interesting one because it reacts to the rotation rate of the helicopter. And you can basically interpret this as a spring that wants to push the helicopter into a turn. So if I give an input on my stick, for example, I command full forward elevator, the P gain is going to push the helicopter into this turn like a spring is pulling on the nose, like pulling down. Now you also have your D gain, which looks at the acceleration and counteracts it. And these two now need to be tuned so that the reaction of the helicopter conforms to what you want. D gain works against the acceleration. P gain works for the acceleration. So you have a P to D ratio that you're now tuning to get the reaction exactly as you want. So you really just take your transmitter and jab the stick. And then you look at how the helicopter reacts. If it feels like it overreacts, you have too much P in the system because, again, that pulls the helicopter into the turn. If it feels sluggish and slow, you have too much D in the system, which damps the reaction of the helicopter. So by adjusting P gain, you can now tune the reaction of your helicopter. How many of you have flown a V-bar? Okay, that seems like most people. Do you know the style parameter? Have you ever wondered what that does? It is just PD ratio. It is exactly that. So if you increase style on V-bar, you're giving it more D, less P. If you drop style on V-bar, giving it more P, less D. The only difference here is it has a different name. So from here on out, you can treat your P just like style. Raise it if it's too sluggish, drop it if it's too fast. Once you're happy with the reaction of your helicopter, you can move on to I gain. What I said was the I gain looks at the angle of the helicopter and tries to keep it in accordance with your control inputs. So as the helicopter is rotating, the I gain will fight to keep the rotation rate constant. This is also important if you're, for example, not just rotating on the spot, because there you don't mostly need the integral to do much. But if you, for example, come in with speed and want to flip forward, the integral actually needs to push the helicopter more than your feet forward would. Or if you, for example, want to pitch up, the integral would have to help the helicopter stay actually in the track you want because it naturally wants to pitch up. So what you can just do is fly, see if during your maneuvers the helicopter tracks the stick nicely. If it doesn't, increase the I term. Just increase the integral gain until it tracks nicely. You might run into a situation where it starts wobbling in some maneuvers. That means I is too high. Then you drop it a bit lower, and then you should be good. Next off, the high-speed integral. That is pretty much a second I term that runs in the background and is responsible especially for flying at high speeds. I'm not going to go too deep into how it does it because the Contronic guys are already looking at me funny. Sorry. But basically, if you fly fast and raise and drop the collective, any helicopter that does not have a high-speed integral, for example, Brain, or as you Americans know it, Icon, is notorious for not having a high-speed integral. So if you go fast and drop the collective, it's going to nose down. If you give it more collective, it's going to nose up. Or if you try to do tic-tocs at speed, any flybarless system with a high-speed integral is going to go nice and straight. Any flybarless system without it is going to like do this one, raise and drop the nose in the direction of travel. So what you do is you increase that one until the helicopter starts wobbling. When you climb out and just give it an input, then you just lower it a bit and it'll be fine. The end goal is to fly in a straight line, raise and drop the collective, and have the helicopter not change attitude while it changes altitude. Again, if it's too high, it's just going to start wobbling, nothing dramatic, just back off a bit and it will be fine. Last one in this is boost. If you have ever used pedal sim on a V-bar, exactly the same thing. It's just a derivative on the stick, which means the faster you move the stick, the more the input is going to be. That is mixed into the control sum, and it's just going to give you a little more jab on the cyclic if you give it a fast input. That is all it does. If the helicopter should be more smacky, like that crack type of flying, you increase B. Otherwise, I like to leave it around 0. I give it a little bit, like 10 to 15, but not too much. And once you've done these steps, first tune D, then tune feed forward. Oh yeah, feed forward, if we go back to the V-bar analogy, that is just your optimizer. The optimizer is just your feed forward, does nothing else. So D, feed forward. P, I, HSI, or O gain as it's called in the Lua script. And then B, if you tune them in this order, the way I described it, you will end up at a perfectly flying helicopter that conforms pretty much exactly to your expectations, tracks nicely, hovers nicely, it's very precise on small inputs, can be flown fast, can be smacked around, will be beautiful. To not waste too much more of the Contronic guys' time, tail tuning. I'm going to go over this real quick because I explained the basic concepts of PIDs before. I have worked out a method that works for, as far as I've tested most helicopters. It might not work for yours. It depends a lot on the tail servo, on the tail blades. But what I do is first I increase D, just like on the main rotor. The idea is to get the tail to kind of shiver on stops. Now this is very different from helicopter to helicopter. I know helicopters that need basically 0 D on the tail. I know some that need like 50 to 100 D on the tail. It's very different. So increase that until the tail kind of gets into a shimmy on stops. Then you start raising P, because P is, in this case, the gain that gets your reaction right and your stops. You raise P until your tail either starts, oh wait, I forgot one thing. After you found your maximum D, you're gonna cut it like in 1/3. So if you end up at like 300, you go down to 100. Easiest example, it will be lower. Yeah. Then you start increasing P until it either whacks on pyro stops or when flying sideways. Important part with flying sideways is that the air needs to flow into the low pressure side of the tail rotor. So for example, you can fly to the left, do a sideways loop. If it whacks there, P is too high. If it whacks on pyro stops, P is too high. You can play with D a bit if it starts wagging on pyro stops before it starts wagging in sideways flight, but mostly just raise it until it whacks and then back off a little bit. The I gain, stupid easy to tune. You just raise it until the tail starts to shimmy a bit in a hover. It kind of becomes restless, starts shimmying a bit left and right, then you drop it. You should be around 200-ish on any normal helicopter at that point. The I gain will also help you do pyro moves, pyro loops, that kind of thing. You might find stops and then keeps creeping. You want to increase your feet forward. In my helicopters that I've tuned, this never happened. The tail would rather stop and then strike back. So you stop and it comes back. What that is the I term charging during the stop. And that is where, oh no, did it lock? It locked. Oh no, it's back. This is where, give me the configurator, oh there it is. Oh no, that's not a configurator. This little field right here, the I term relax comes in. If you have strike back on any axis that you cannot eliminate with the other tuning parameters, you want to lower your relax. Joanne is going to kill me for this. He hates relax. I found it necessary on my helicopters. So if the tail just stops and strikes back, you lower the amount of I term relax until it stops. I'm not going to go into why that is. It's just a filter that you put the stick signal through, compare it, and then inhibit the charge of the I term. But yeah, just drop relax and it'll be basically fine. Same thing also on the cyclic. If you encounter, for example, strike back when going fast and giving an input, and it just pitches up and then pitches back down. That is also when the relax is too high, so drop that a bit. And yeah, for the tail, the last thing you can do is adjust the boost amount, just like on the main rotor. It's just a derivative of the stick, so if you want it sharper, you can increase the boost to give it that extra bit of pop. But given how sharp Rotorflight's tail is, I've never actually used that on the tail. Last thing for the tail, if you come all the way down here, you will find the pre-comps. And the only pre-comp you really need is the collective feed-forward gain. You increase that until the tail does not wiggle anymore on collective. Like, for example, if you punch in collective and the tail wiggles out a bit to the left and then comes back, that one needs to go up, collective feed-forward gain. It's the same as torque pre-compensation on a V-bar or any other flywheel system. Every single flywheel system has it, basically. So you go from there until it does not do the little shimmy. If it's too high, it will actually strike a bit to the right first and then come back. So tune that until it just climbs out straight. If your tail is very asymmetric and has more thrust in one direction than the other, oh, this thing is on. So for example, the M7 is actually like that. It has like 44.5 degrees against torque and 31.2 degrees supporting torque. You might actually find that your pyro stops are different in each direction. Then you have the stop gains, clockwise and counterclockwise stop gain. And you can just tune them. If one pyro stop is softer, you raise the stop gain. If one is too hard and wax a bit and the other one is soft, you just drop it a bit. And I guess that is basically it for getting a basic tune going for your helicopter. I think the Contronic guys are waiting, so I will say thank you very much.
Thanks, Jonas. Thank you. Thank you, everybody. Great job. Thank you, guys.
Thank you.
All right. Thank you to Rob, Bob O in the Discord for Rotorflight, Jonas, and to Joanne, who is Itaki in the Discord as well. All right. So we've got the Contronic guys waiting, but thank you guys for